Good morning.
Hey, good morning. Good morning, guys. Ashwath, where were you last class?
Yeah, Professor, like the last week and a half, like my grandma's not been feeling too well, so like I had to go back to like the Bay Area. So that's just like why, I haven't been able to do the work, and now I'm back. I came back yesterday. So yeah.
Okay, so she's better now, I hope.
Yeah, she's feeling better now.
Okay,
Yeah,
so you can focus, right?
exactly. Yeah.
Okay, so you got to put in a lot of work now because we covered a lot of stuff, and
Mhm.
and you have to catch up. Okay,
Got it. Yeah, I'll
there's
be
a
that's
lot of work. You're majoring in computer science too, you said. Yeah.
I mean stats and data science. Yeah,
Yeah. Okay. Well, if you're doing data science, you got to know, computer science.
exactly.
So
Yeah.
yeah, okay. So yeah, I'd be expecting you to because even a few classes ago, if I remember correctly, um, we were all coding, and then um, from your Zoom rectangle, you were it sounded like you were watching a game on TV or something because you were cheering on some players and all. And so you got to put your whole attention into this class, okay? You can't
Yeah.
let these other things interfere. You have time for all of those later on in your life. And yeah, so basically, otherwise you're not, this class will be wasted. Anyway,
Okay.
we'll start at 8:10 or something. And you guys should just feel free to talk. Noah's here too. Nobody sent me um, the code we were working on before, the special effects code. So I'm not going to host that. So at the moment, the only thing I'm going to put in the folder as winter 22 achievements students is that are the lucky packages that 3 people have sent me: Ashwath, Kai, and I think one more person. Yeah.
I sent you a story. Lucky.
Who?
I
No,
did.
no, Sean, you didn't send me lucky. Did you?
I did. Yeah.
Okay, maybe those are the 3 then. I thought I had one more than you then. Maybe 4. Anyway, I'll see. Okay, so send me this other thing too. Whoever has the code, I think maybe Keenan has the code. Okay, or Keenan or Noah, I keep forgetting because those were the 2 guys who were coding for the special effects. So we have at least 2, right? That the class has worked on. Was it what we did? Yeah, the class worked on 2 special effects. The marquee one, that's scrolling left to right, and the other one was shuffling into place, right? So at least those 2 methods are there. We're going to put them up there. We will put them in the file with a comment saying these 2 were created by the whole class. Okay. In addition to that, if you can send me your own animate methods, we can add those 2 also. So you have animate marquee, animate shuffle, animate explode, and then a comment could be animate explode was created by Ali, right? And animate something else, and so on and so forth. Yeah, is that okay? All right, so send it to me at least this weekend, okay? I hope to get set it up this weekend. So I think the main reason is I'm waiting to get more stuff to put there. Not just these 2 projects, and nobody's sending it to me. Maybe that's why I'm just putting it off. But this weekend, if I'll just put it there because it's getting to almost the end of the quarter, and those who have to catch up have to catch up. Okay, um, you got to get serious about this. So today I'm thinking what we'll do. Actually, I had this idea this morning because I think we were working on search techniques last class, and you also got a search, a linear search to work, if I'm not mistaken. Yes.
Yeah.
Yeah, you got. So we can review that code really, really quickly because I'm pretty sure it looked good, but I didn't check the search method itself. But I'm pretty sure I'll take your word for it for now. But we'll take a look. It's only like 3 lines or 4 lines, so we'll take a look, and then I was thinking, let's search an array, a vector of integers, for another integer. And then I don't know. So I think that many of you will eventually go on to do data science or data engineering or in computer science dealing with number crunching at some point anyway, right? So if you guys are okay with it, I think what we can do is this. I can basically turn this class into lecture 0 of my graduate level machine learning class, which I used to teach in a previous life a very long time ago. But I figured that, you know, that lecture 0 is not something that's beyond cs2a students. And it is, in fact, the basis of all machine learning, most machine learning. Okay, I shouldn't say all, right? Most machine learning and data science algorithms come from this kind of insight. And I'm thinking this is what we'll try and do today. So we're going to say, here's the plan, okay? And you guys correct me, or, you know, tell me if you want something else. Here's the plan. We have an array of a huge array, let's say 10 million numbers, okay? 10 million numbers in there. And now you don't know anything about the array, okay? I just say, here's an array of 10 million, and I pass it to you by reference, a vector. Now, so far, are we all on the same page, right? I pass to you a vector of many millions of numbers by reference, so that you just get the address. You don't get a copy of the vector, okay? So
Yes.
you now have access to that vector, yes or no?
Yeah.
Okay, good. Now I'm also going to pass a target string, target number, okay? I'm saying, and I'll say, is this number in this vector or not? Okay, and this number could also be very large, so it's not. So, and you're going to do linear search, yes? And I think that you already have the algorithm to do linear search, because last week you were doing, you know, last week, I keep saying last week, it's Tuesday. You were doing linear search on strings, yes?
Mm-hmm.
Yeah, so it's exactly the same. You're just going to do linear search on numbers, yeah? So now that is the case when you don't know anything about the numbers in the vector. Now, suppose you had some inside information, right? Someone told you these numbers are all even numbers, okay? There's no odd numbers in there. Now, do you think that will speed up your search? You got a bit of information, right? You got a bit of and do you think that information is useful? Let's put it that way, okay? Do you think that information someone gave you about that vector is useful in your search or not?
Wait, can you repeat the question?
Okay, so the first thing that you've done already is that, you know, if I give you a vector of 1 billion integers, yeah, and a target number saying, and I want to know if this number occurs in the vector or not. You have already written a method. Last class, you wrote a method to search the vector and tell me yes or no. Okay. Now,
Yeah.
you know, it's going to take a bit of time, right? Because if the number is large, you got to search lots of numbers. Yeah. Okay. You can do it faster than that. Can you do it faster than that?
Yeah.
No, you can't change. You can sort the array and all, right? Sorting the array is not allowed, because if you sort the array, if I ask you for a number and then you say, I'm going to sort the array and do binary search really, really fast, you're actually slower than I expect, because I expected at least linear time and you're giving me the result in n log n time, which is fast, slower than linear. Yes or no? My first call is going to be n log n, isn't it?
Yeah.
Yeah. Okay. So you can't change the array. So I've given you the array and I've given you a number. And you say, I can give it to you in linear time, whether the number is in the array or not. So can you do better than that? Okay, so that, you know, I don't know, maybe you can pass it on to other students who are also interested in majoring in machine learning and data science kinds of things. This is the core insight you have to identify and start nurturing, because that is a seed that will flower into different kinds of machine learning algorithms and thoughts in your head, okay? So we're saying we don't know anything about this. Can you do better than random? Well, in this case, you know, random essentially is basically searching every number until you hit it. right? So you're going to say, can you do better than that? Can you do better than a trivial solution, which is basically going to step through everything until you find it? That's going to take linear time, right? If my number is at the end, it's going to scan the entire thing and find it, or it's going to, even worse is if my number is not there, you got to search the whole thing and say, no, the number is not there. Yes? So it's really crazy.
Can you like find out like what type the number is, like whether it's even or odd or divisible by something,
But you know,
and
but
then
if you
just
didn't
factor it
know
out?
anything about the array, if you, oh, are you saying find out something not about the number, find out something about the array? Fine, you're saying you don't have any control over the number that I'm going to ask you to find out. Right? I'm for this,
Right.
so, right?
Right.
But you have an array. But what you can do is you can look at the first few elements of the array, maybe the first 1,000 elements of the array, and say that, okay, well, you know, I got to search this really massive array, and I don't know if I have time for that. Tell me if this is how humans think, okay? Because I think like this, and if you think differently, you should tell me. I think that you think this way too, okay? Oh boy, I got to search this, you know, a huge, massive array, and I really wish I don't have to. But this number I got to search. But let me first look at the first 1,000 items to see if there's any pattern in the array, and then I can look at the number, and maybe, you know, just that pattern is enough to tell me, tell them the answer without having to look through the entire. Is that a reasonable thing that humans will do?
Wait, look at the array for patterns. I'm not really sure.
Okay, so you know, it's okay to take time to understand this. Okay, don't worry, everybody. Sean is the only one who's speaking up and asking questions. Okay, but these are critical and core insights, especially if you're planning to major in data science later on. Okay, so feel free to ask away. You got to get to the very bottom of this. The problem is this: you've been given. This is the problem in machine learning. No matter what you're trying to machine learn, right? No matter what what pattern you're trying to identify, whether it's 1 dimensions or n dimensions, you know, virtual space, it's all the same. You're trying to discover a structure so that you can ease your own work. That's all. That's all there is to it. Yes. So if you have a massive array to search, and someone comes to you with a number saying, is this number in the array or not? As a human, this is what I would do. I take a look at this number and then take a look at the size of the array I got to search. Yes. and I say, oh man, yeah, I hope I don't have to search this whole damn thing for this number. So let me look at the first few numbers to see if there's any pattern, so that, you know, I can tell from the pattern itself whether this number is going to be in the array or not. That is what I hope for. Yes or no?
Yeah.
No, okay.
Yeah.
Nodding.
Yeah.
Sean said yes. Ali, do you agree with this or not? Everybody needs to say this, okay? Everybody needs to be on the same page, because this is what we're going to do today. This is what we're going to do today, right? In code. This is why it's machine learning lecture 0, right? You can go on to do advanced machine learning courses too, but if you have this in your pocket, everything that some other professor says will actually make total sense. When you're sitting at the lecture hall, at your lecture desk, listening to them, and they explain.
I follow so far.
Yeah.
Yeah, we follow. Yeah.
So Van, do you say you understand too? You're okay with this?
Oh yeah. So far, yeah. So far, so good.
Zain, you good too? Justin, Ali, you shouldn't say yes just because everybody else said yes.
No, I know. I was saying, could you repeat it?
Thank you. All right. Well, let me go over Noah and the other two also, right before.
Yeah, I'm
Kai,
good.
repeat or you're good? Noah, repeat or good?
Yeah, I'm good.
Kai,
Kai,
are you there?
Yeah, I'm good.
Okay, good. I'm going to repeat this for Ali and also for the sake of someone else who's not here. Fernando, where the hell is Fernando? Right, he's just making it in and out of these classes. There's no way you can pick up cs2a like that, okay? And then if you don't do that, you're basically going to take up like a ton of time from your tutors. Yes? You're going to be sitting in the STEM center and monopolizing the time, and you're going to fill in that spreadsheet saying, okay, I got the next hour of the tutor, and it's a waste, right? This is like a golden opportunity, right? Don't waste this time and come to classes, okay? Pass this message on to Fernando and all these other people also, right? Anyway, so Ali, here's what we're the plan. I'll explain this slightly differently, okay? So imagine I have a huge hotel full of rooms. Yes. Hey, Kaylee, this is the problem. Okay. And since you joined late, this is the problem we're talking about. This is the basis of all machine learning, what we're going to do today in class also. And we're going to take searching from the previous class. Okay. And all right. Okay. So the problem is this. We have this vector is really, really large, millions and millions of numbers in it, numbers. Okay. And you can think of this as a hotel, and you're the receptionist or, the manager of the hotel, and there's lots and lots of rooms. Yes. Okay. Now someone comes in and says, is there a free room in the hotel? Yeah. Or what's in that, right? This person likes to stay in room number 6,432,000. Right? That's their favorite room because that's got a great view. Right? So they come in asking, I want to know if 6,432,000 is occupied or not. Right? Now, assume that you don't have a computer or you don't even have a bellboy to say, hey, go and find out. Okay, you actually have to go and check yourself. And there's no quick way to go from room to room. You actually have to go from one to the other. Okay, so you got to walk 6 million rooms and knock on that door to see if there's someone in the room or not. Okay.
Oh, so it's like a very inefficient process.
But that's what you're doing with linear search. Yes, because thank you, man. But that's what you're doing essentially, right? You have a vector of students, and a random student comes in and says, am I in the list? You're going to scan your list from the beginning. Is the student in cell number 1, cell number 2, cell number 3? Okay, if you don't find them anywhere, you're going to say no. If you find them somewhere, you say yes. That's what you did last class. Yes or no? All right. Actually, a few people are nodding your heads, but some of you have your camera switched off. And again, please, I know Kaylee was on camera before. As much as possible, turn your cameras on, because the lecture also, the Zoom looks much more colorful that way. Not that people are looking at the videos, but still, if there are future students who want to look at these videos, it'll look much better. Now, so far, is everybody okay? I want to make sure, Ali, this is what we did last class, right? You're doing linear search, and it's really efficient, right, Ali? Yes, inefficient because you got to look at every single one. Yes or no? It is the same thing with a vector. So I have a large vector, and I have to look for this number. The only way I can find it if I don't know anything about the vector, I don't know anything about the vector, okay? It's all random numbers. I don't even know if they're ascending, descending. Even if it's ascending, descending, I can leverage that information. Yes? Yeah. Okay. So I don't even know if it's ascending or descending, or sorted or non-sorted. So I just know there are a bunch of random numbers. The only way I can find out if that number is in the vector is if I look at each element until I find the vector, the number, and say, yes, the number is there. Or I've reached the end of the vector and I never found the number. Those are the only two ways I can find out. Yes. Is there a better way?
Did you say if it's sorted or not sorted?
It's not sorted. It's all completely random.
Can we call a function define for?
Yeah, but the find is still going to do the hard work for you. Yes.
Sorry, say that again.
If you call another function to do the find for you, yeah, in the vector.
Oh yes, yeah. To call another.
That function is still going to do hard work for you. Yes.
Oh, it would still be pretty hard. Okay.
No, it's not. I'm not talking about the amount of work. It's just saying the amount of CPU cycles, meaning how long it's going to take before you get the result.
Yes.
Whether it's your function or someone else's function, it's basically you just have to wait.
It would take a lot of cycles then.
It will take a lot of cycles. Yes. So I wanted the point I'm trying to get at is that if you didn't know anything about the numbers, if you didn't know anything about the vector, I don't think you can do faster than linear. That's this inefficient thing is the only thing we can do.
Oh, I see. Okay, so even with that 6 million number, the only way.
Right. Yeah. If you didn't know anything about the thing, if you didn't know anything about the vector, and someone asks you, is this number in the vector? You can't do better than looking at every single one until you find it or not find it at all.
Oh, okay. Yeah. And so what you're saying is that that's our best.
That is your best. That is your absolute best if you didn't know anything about those numbers.
Oh, if you didn't know anything.
If you, okay.
I caught the if. Okay.
All right. Okay. It's okay to spend a lot of time on this really because this is the rock solid foundation. Okay. This is the basis on which every single thing is going to be built later on. So it's okay to understand, but this is where we're starting from. We're starting from linear search. So, it's things that we do later on should not be worse than linear search. It can be better. It shouldn't be worse. Right? It can be as bad, but it can be worse. Yes?
Okay, yeah, makes sense.
Okay, all right, good. So that's why it's so important to know the limitations. Every time we go to the next step, we want to know what's the maximum height I can reach with this step. So we want to know the limitation of linear search and have that really ground into our skull. Okay, say linear search I can do in my sleep, right? And this is how slow it's going to be. I can't do better than that if I didn't know. Okay, so as long as we're all on the same page, I can make that next point now, which is going to be the basis of machine learning. Okay, so we're on the same page now. Ali, can we go on? I can talk about the next point. Okay, so here, so if I had a problem like that, and I knew that the best I can do is linear search, which is a real pain. I'm talking about this like a human. Okay, if linear search is a real pain, and someone asked me, is there this number in this vector, and I know I got to do linear search on it. It's a real pain. As a human, am I not naturally inclined to think, is there an easier way to do it? Can I, right, without having to look through the entire vector of millions and millions of items, can I just look at the first few numbers and make a guess, an educated guess, right? And say with certainty to this person, well, almost certainty anyway in this case, right? But in this case, with machine learning, by the way, we're into the way, we can't have induction anymore. I don't know if you know about induction and deduction in science, right? Two different kinds of argumentation. A deductive truth is guaranteed to be true if the premises are true, right? An inductive truth is, most likely true. Like if I say the sun will rise tomorrow in the east, that's inductive truth, right? Because, it's been conditioned by years and millions and years of humans looking at it, and it's all in the data, right? Highly likely to be true. Right, but if I say that all crows are black and this is a crow and therefore this is black, then if all crows are black, this crow has to be black if it's a crow, because if the premises that are true, the conclusion has to be true. That is Sherlock Holmes, although he does induction. I'm fond of saying that, right? He's called a deductive guy. He just does, he's not deducing things. But he's just making.
So you're saying then that in machine learning there's some sort of like inductive type of.
Oh yeah, exactly. Machine learning is basically empiricism brought to logic and computer science, I think, in the sense that we're saying now we're not after the absolute ground truth, but we're after utilitarian practical truths. And how you get at it does not really matter. I'm not after a coherent mathematical model as long as the output matches what I want for this set of triggers. Right? And so you kind of let the system learn what the pattern is. That's what I mean. It's a structure identification. Once you feed it a lot of data, and again, when you do machine learning, you'll see that, if you just feed a really sophisticated system, the top of the line system from, Pentagon, the Pentagon or DARPA, you get the best possible machine learning system running on a supercomputer. But if you give it a lot of trash data, it's going to, it may not even converge. It may not even find the right model. Yes, because it's just too much noise. So one of the things that this kind of exercise, what we're doing in class helps us is to train good computer scientists and good machine learning engineers, in the sense that if you get given a 24-cylinder car, you should know how to drive it, in the sense, right? So if you get given a supercomputer and a super duper good machine learning algorithm, then you should be in a situation to say, well, you know what, I've got this really fantastic thing. I should make the best use of it. So I'm going to check the data and make sure that I can inject as much human intelligence into the data as possible, so that I can remove all the noise, so that the machine learning system will have a much better chance of converging to the actual pattern that I suspect is hidden there. Yes or no?
Yes, yeah, definitely.
Yeah, and so now how what we're trying to do with computers and machine learning has actually become empirical science, right? It's not really mathematics anymore, because people who do machine learning and data science, they're not mathematicians in the computer science sense of thinking about it, right? In my opinion, I think it's bifurcated at this point, because pure computer science is truly mathematical. It's based on deductive logic. You can prove things. You can prove things about algorithms, right? But once you go on to data science and machine learning, we are interested in average behavior, most likely behavior, and things like that, right? And you want, thresholds of likelihood, 99.99s of the probability that this car will make a turn here and not crash into something else, That's what we're after. We can't say 100% anymore.
Sure.
So
Okay.
that's exactly what physics and empirical sciences do. You can get better and better microscopes, telescopes. You can get to the very heart of what we think is matter. We still find smaller things, right?
Yeah.
And keep going on and on and on, right? Because it's all empirical. When you observe something from the outside, there's also always a limit to how fine you can go. It's only as fine as our measuring instruments let us go. And the physical constraints we have to face. So with machine learning, what happens is that the best machine learning engineers are also the best scientists, empirical scientists. So if you're a good machine learning engineer, you'll actually be very, very good at physics, chemistry, all of these things. Why? In my opinion, it is because you get really, really good at identifying patterns. Okay, and science is nothing but identifying patterns in nature. Okay. So when you say that, an apple falls to the ground all the time, let me see if there's a pattern to it. What is a pattern? You could say, well, one of the patterns is the apple always falls to the ground, right? That would be a newbie kind of pattern to make. Yeah, okay. But then you get bored by that pattern after a while and say, oh, okay, well, you know what? I got a pattern. If I drop it, it's going to fall down, and it's predictable. It's a pattern. It's boring after a while. So you say, well, is there a higher level pattern here? What's a higher level pattern? Okay, let me see if there's a pattern to how long the apple takes to drop if I drop it from this height and that height and that height and that height and so on. Yeah. Now you get lots of measurements at different heights. Is this not what you do in physics, right? Finding the period of a pendulum, right? Change the height and oscillate it and see how long it takes to, period of pendulum. Physics experiments, does it ring a bell? Chemistry and all these things.
Yeah,
These
that
are
was
lab
pretty
sciences.
tough.
I don't know. When I was a kid, we were doing lab experiments, back in India, I think, and our school lab was open even during on Saturday and Sunday, and anyone can come and play. And I was there, with all the electrical equipment and pendulums and things like that. So and chemicals, under supervision. So, but it's fun. You should try these. I even when my daughter, this was like just I don't know, like 15 years ago. Was it JLS? Yeah, she was in JLS, and her student and her teacher, Kevin, physics teacher, and he made the class do experiments to this experiment. And I remember the experiment was to actually figure out machine learning. Really, he was trying to get 7th graders. My daughter was in 7th grade. Okay, and he was trying to get 7th graders do machine learning. Right? But then maybe they don't recognize that, but that's what they were trying to do because I knew that's what he was trying to get them to do because I had a blast doing it with her. Okay, so he said, try and find out if there's a pattern to how long a pendulum will take to oscillate if based on the length of the string. That's all. Okay, and so we just had to create a table of if the string was metric system, I don't know, 1 foot, 2 feet, 2 feet, 3 feet, 4 feet, how long it took. And I remember, oscillating the pendulum from the top of, my brother-in-law's house, all the way to the bottom of the, to the street and measuring the time. It was all really great stuff. That's what we're doing, right? So what are we doing there? Exactly what we're going to do in class today, right? We're trying to design a pattern. We're trying to see, is there a pattern so that I don't have to remember all the details. So tomorrow, if someone tells me, I have a pendulum that is 4.7 miles long, okay? How long is it going to take for one oscillation? Now, I know if someone asks me that tomorrow, I know, wow, I don't want to get into the business of making this long pendulum and going up to the top of some, Eiffel Tower or something like that and oscillating it. Yes, under controlled conditions, it's going to be a pain to do that. So let me see if I can figure out a pattern to all this. This is what Newton did. Yes, and many scientists before him too, obviously. Yeah, in various civilizations. So you look at these things, find out a pattern, and say, well, okay, the pattern in the apple being dropped is that it is actually gaining velocity as it goes down. Because that's the only thing that can explain it, right? The Copernicus and the Kepler model of the universe and things like that. So they come up with a theory and say, okay, now let's try and figure out what the pattern is. And so now we know the pattern. It's the acceleration is 9.81 meters per second squared. Yeah, and therefore now that I know the pattern, I don't need to remember the entire vector of, an infinite, a countlessly infinite number of heights from which the apple could be dropped. You can tell me. You can ask me how long the apple will take to hit the ground when it's dropped from 8 meters. I'll tell you like that. I don't have to actually do it to tell you. Yes?
Okay, yeah.
Because
how
I
do we-
found
wait,
a pattern. I found a pattern.
Okay, so then we're gonna be finding like to transcribe that to today's lesson is kind of like finding that in machine learning somehow through C++
Yes,
vectors
yes,
and
that's
stuff?
exactly
Okay.
it. That's exactly.
Okay.
So that is what it is. Okay. Here we've got an array, and the machine learning 0 is to say, what can I do with the array? So that one thing is, I don't want to search the entire array. I don't want to look at the entire array to find my pattern too, because it's the same complexity. Where's the same amount of badness in time. Okay. Can I just make my job easier by looking at the first few elements and forming a theory? Yes.
I mean,
No.
that does make sense, but if we're looking at a vector, what's the components of the vector?
Yeah. Okay. That is what we're going to do today. Now.
Okay.
All right. At first, we don't know anything about the vector, which means there's nature out there. We didn't have any physical laws. So we have no idea what the hell is going to happen next. Yes?
Yes.
Okay. All right. That's a child just being born into the world, right? No, everything is a surprise. No predictions at all.
Okay.
However, you have that vector, and even though you cannot change the vector, because Noah said, yeah, if I sort it, I can do some clever things. Okay, you can't change the vector. Okay. So, but I have the vector. It's a const vector, but I have it. That means that over a period of time, I'm going to keep looking at it and start getting an idea of how the vector is structured. Yes?
Okay.
Okay. Now, after the first few thousand times, people have asked me if there's number there, I keep searching, right? And even though I haven't searched till the end of the vector, after the first few items, I'm almost certain if that item is going to be there or not. Why? Can someone give me an example?
I actually think I saw a TED talk on this where you can find like the pattern.
I don't know. Well, people have been talking about this for millions of years, thousands of years anyway, right? Because it's basically just pattern induction, right? It's just trying to find pattern.
Mm-hmm.
Yeah. So but here, what was I saying? Tell me, give me an example of one piece of information you can know about the vector, right? Or one thing you've discovered about the vector, so that you can give the answer instantaneously. I'll give you one example, okay? All right, so I have this vector, enormous vector, billions of items, and someone tells me, does this vector have the number 6,475? Okay? Now, my choices are, okay, I'm gonna start looking, 1, 2, 3, first element, all the way. We know that's the most inefficient way. However, I see the first element is 0. The next one is 8. Right now, I'm going to keep going. I'm going to keep telling the numbers, telling you the numbers that I see in the vector. As soon as one of you has identified the answer, you should say yes. My function can return right now. Okay. Basically, you're going to press the buzzer and say yes. Okay, this is a game. All right, this is a game in which I'm going to keep telling you the sequentially. Vector 0, vector 1, vector 2, each of those numbers I'm going to say, right? As soon as one of you know the answer for the question, is that number 6,345 or whatever it is, right? 6,345. Can you write it down? Hey, guys, please can you switch on your cameras if possible at all? Right? The screen is starting to get very boring. There's just too much gray, and it kind of looks very boring after that. All right, so I'm going to reel off these numbers one at a time. And the first person to say, I've got the answer, okay, has actually identified the pattern. Okay, best machine learning engineer. Okay, says, I've got the pattern. All right, so I've got the power. Okay, what is the number, by the way? Have you all written it down? 6,345. Okay, so that's.
Wait, sorry, did you say billion or million?
6 billion, 6,345. Okay, that's the number we're after. Okay, so the first number is 0. The second number is 16. The third number is 473, 474, 474. Okay, just write it down. Just write it down. Don't try to pick out the pattern in your mind. Okay, then you'll forget what the previous numbers were. Okay, the fourth is 474 because I don't know what the numbers are, but I know the pattern, so I don't remember what the numbers are. You should write it down. Okay, 474, 2,106, 2,312, 18, 56, 2,642.
Would it be
Two.
safe to say
Wait,
that
wait,
your number doesn't exist because the
So you've got the answer. Who's this? Who is this, by the way?
Justin?
Justin. Okay. All right. So you press the buzzer. You want. So you press the buzzer. You want to give me the answer? Yes or no? Right? Does my number exist in the vector or no? Not.
It wouldn't exist because the vector is even.
Who else? Who else has the same answer as Justin? Kaylee.
yeah, I would
Yeah?
say so.
Yeah. All right, Sean. Okay. Anyway, as it turns out, thank you, Justin. Okay. Fantastic. As it turns out, that was a pattern I had in my head. Okay. All even numbers. But you didn't know that, yes?
No.
All right. Because now here is the thing. Here's where that line that many people don't see has been crossed. Okay. This is the line between the mathematical aspect of computer science, mathematics, pure mathematics and logic. You're in, well-grounded territory that you know for sure. The ground under you is solid, essentially. You've stepped over the line now onto a minefield, essentially, where the ground under you is not guaranteed anymore. That is science, empirical science. Essentially, what's happened is that you've left the internal world and gone on to the external world, where the external world, things are out of your control. Shit happens. Yes? You don't have control over everything that can happen around you. So the moment you leave your internal world and go to the external world, you should be prepared to say, all right, okay, I'm venturing into uncharted territory and I should be prepared. If you accept that, everything will be fine in the external world. Okay, so that has happened. When Justin said that number does not exist, he left the realm of mathematics and went into the realm of empirical science. Because who knows? Maybe that wasn't the pattern in my head. Maybe the pattern in my head was the first 5,000 numbers should be even. The next 5,000 numbers should be odd. Yes? So you don't know. However, there's a very, very high likelihood that I'm, all even. Yes, because and in fact, the more numbers you examine, the more sure you can be. Okay? So coming up with that hypothesis, it's a hypothesis, not a theory. A theory is something we know for true. Well, I don't know what the different definition is really, but in my mind, a theory is stronger. Okay, it's like a mathematical theory. We know for true. It's deductively provable, right? A hypothesis is something. It's a theory, but it's very likely true, right? There's slim chance that it could be false. That's an inductive truth, not a deductive truth. This is all useful to you guys because I think it's related to computer science and cs2a. Okay, that's the reason I'm talking about this now. If you don't want me to, I won't. But this is what we're going to implement, okay? When someone picks up the code, what we're going to try and implement is basically we're going to have a vector. And in that vector, and I'm thinking, this is the idea I had this morning, okay? We will inject a pattern that we don't know, okay? And our job will be to write a function which can discover that pattern and do some clever search, okay? So in fact, we're not doing linear search and we're not doing binary search, but we're doing something called something really clever called heuristic search. Okay. And I don't think there's, other people will teach you this. I don't know of any other class that teaches you this because I didn't have this idea until this morning in the shower. Okay. So I think this is really cool. This is a heuristic search in which you get given a constant vector. Okay. And a target number. And then you got to look at some fixed number of elements in the vector, form a hypothesis, and then give me an answer, which you may or may not know is correct, but will have a likelihood of being correct depending on whether your pattern is correct or not. Okay. And however, we'll make the pattern not like true, professional grade machine learning, because in professional grade machine learning, what are we trying to do, right? First of all, we get comfortable with these simple problems like 1 dimensions, 2 dimensions, 3 dimensions, and so on, right? So when you're comfortable with this, this is what is going to happen. We'll say, okay, now I'll just use this toolkit, which is basically going to take what we already know and apply it to n continuous dimensions. Yes, exactly the same thing is going on. Just like, if you know the Newton methods for, I don't know if you've already learned this in math, maybe you learn it, right? There's a way to find the minimum of a parabola, minimum of a curve, right? Without actually knowing the equation of the curve. Do you know how to do that? Well, you can do that using a computer too. Maybe you can do that in a later class. So suppose you have tell me if you want me to stop talking about this. Suppose you have a curve, okay? A parabola. Let's just take a parabola as an example. Please stop me if you don't understand any of this, right? If you're not majoring in math or don't understand this, tell me and we'll move on, okay? Suppose you have a parabola and you want to find out the minimum here, okay? And you don't know the equation. One way you can do it is start anywhere, any random point, and take the curve. There's a slope of the curve at that point, okay? If the slope is pointing downwards, you just move to the right a little bit. If the slope is pointing downwards, move to the right a little bit, okay? And keep doing that. As long as you take small enough steps, at some point you'll be close to the minimum, where the next step you take is the slope is going to be 0 or greater than 0. Yes. Now this is basically the intuition behind. I know in mathematics you might have done minimum and maximum by taking the first derivative and setting it to 0. That's what you're doing, right? You got a parabola. You take the first derivative, set it to 0. You find the minimum. And what is the first derivative? It is a slope. The slope is 0. The slope is negative here, and the slope is positive here, so it has to be 0 here. So you take the derivative and set it to 0 and solve for it, you get the minimum. But if you didn't want to do the derivative in the complex math and the calculus, you can say, okay, I'll just do it the numerical computational way and say, I'm going to start somewhere and take little steps along the gradient. Basically, you have start on a hill, okay, gradient, and basically just ride the gradient, right? The gradient is a slope. So descending a slope is gradient descent. Lots of people say, oh, I do gradient descent and shit like that. It's all just fancy terminology. Gradient is a slope, and gradient descent is descending a slope. So when you identify a slope, right? When you identify a curve that has a slope, just travel in the direction of the slope until you hit a minimum. The risk there is that there may be many minimums, right? Because you can have a complex surface with lots and lots of minimums, and some will be really deep and some will be shallow. So if you take these small steps, you have the risk of getting stuck in a small local minimum. Yes. Whereas the deep minimum might be right next to you. So those are challenges you can overcome, but that only happens in complex surfaces, right? If you have a simple parabola and things like that, the pattern is simple. But once you understand how this works and you understand the challenges of taking, small steps, then you introduce ways in which you can deal with this and other machine learning algorithms that say, well, exactly the same way as programming languages evolved, right? We started with assembler, had some challenges, and say, use this language, that'll take care of that. Now use Java to take care of memory management, things like that, right? Same way, machine learning too. Start with something like this, searching a vector, right? Discerning patterns, and say, oh, well, do this method, because this thing you're doing so often is now taken care of by the system, right? Automatically modeled in the background math. And things like that. So you basically set to choose, right? You can say, this is the kind of data I'm dealing with. This is a n-dimensional matrix, or a picture, a cube or something like that, and that needs to be crunched, and a pattern should be discerned in that. I can see the pattern in 3-dimensional space, but if you project that into n-dimensional space with all those colors and everything changed to distance coordinates, maybe you see something. So, but we don't have the time to do that. So what we say is yes, thank you.
I have a quick question. So when we're talking about the pattern, is it better to, wait a little bit longer and, make sure that the pattern exists, or
fantastic.
Save
what a
time?
fantastic question, right? So this is a fantastic question. Thank you, Kaylee. Okay, because that is exactly the decision that faces professional scientists today, right? At CERN or any of these, NASA, JPL, whatever it is, right? How much money do you throw at a problem before you make your final decision? Yeah. And so at some point you have to draw a compromise. Kaylee, I'm pretty sure most of you have this question, and you'll run into this as professional researchers too, right? And so you'll say, I need to collect this much data in order to make my, in linguistics, right? I need to collect this much data in order to make my hypothesis about this population or how the language diverged. Now, in order to collect that data, I need to stay in this particular, location close to North Dakota for 15 years. I don't know, right? But I don't have time for that. But the government is willing to give me enough money, a grant, NSF grant for 1 year. So now I say, okay, well, you know what? Ideally, I'd like to look at 5 billion elements, but I've only got enough money to look at 10 elements. So also there's always this tug of war, and then scientists will always try and push to say, get me more money because I want more data. And the government will always say, we have experts that say that's all we can afford for now. All right. So, and then a line will be drawn. And that's usually the manager's decision. So most of the time, as a professional scientist, fortunately, many scientists don't have to worry about that. Okay. So even in full research institutions, many labs have the luxury, not all the time, because sometimes I know, right? Sometimes in labs, you won't have some person taking care of your grant proposals and things like that, right? Individual researchers have to do a lot of this, but I know in many places, you'll have people that can take care of these things, talk to the government, even schedule things for your project and take care of the project management, right? That headache will be lifted off you. And you can basically say, go to that person and say, how much data can I get? And they'll say, well, for this much money, that much, you can get that much, right? And then using that, you can assemble all your resources and say, okay, well, for that much, I can get 5 researchers in the field, okay? And this person can do that, and that person can crunch it and zip it up for us. So that's how you plan it. You don't have to do more than that as a scientist. If you're a good scientist, that's all you can do. That's all you need to do. You don't, but if you can't do all of that, then you may be forced to do more desk work along with your, research. All right, so that's basically it. That was a good question, Kaylee. So essentially, that's what we're trying to do. Okay. So what we'll do today is this is the idea I had, and you can feel free to correct it later if you want. What time is it? Yeah, we got a lot of time. We got a whole hour. Okay. So what we'll do is that our vector of numbers. I hope you're all comfortable with this because this is high school mathematics, and let me know if you're not. Okay. Let us just pick a random quadratic with integer roots. Does that make sense? Okay. So in fact, even a equals 1. So what we're going to do is consider the quadratic equation x squared plus bx plus c. All right. A equals 1. X squared plus bx plus c. So there are 2 random numbers there, b and c. Pick a random number between 0, maybe even 0. Who cares, right? 0 and 10. 1-digit random number for b. Another random number for c. Okay. You don't know what the number is. I don't know what the number is. Only the computer will know because you're going to SRAND everything. Now you're going to use that quadratic that you just created randomly to generate all of your vector elements by saying vector of 0 equals, vector of 0 will be a random number with that is generated using 2 randoms for b and c. Vector of 1 is going to be another random number generated by 2 other randoms for b and c. Yeah. So every one of them is going to be a different random number. Okay, that is your vector. And then if someone comes in and says, here's a number, can you find it? Now, how can you find it? Okay, so that will be an interesting challenge for you because all you have is a vector of numbers, but that there is the secret that that you paid a lot of money for to say someone gave you some backdoor information saying, hey, you know what? This is not a true random number list. These numbers were all generated using this underlying generator polynomial. Okay, it's a fancy 2 words for it. Underlying generator polynomial. Because a generator polynomial is basically x squared plus bx plus c, and you just pick randoms for b and c, you get a new number. Yes, for each x. So and someone tells you what that number is. And in fact, someone doesn't even have to tell you the exact equation. They just say this is the form of the equation: x squared plus bx plus c. Now, how many of the numbers do you need to examine before you know what that polynomial is, right? And then you can find out if that polynomial has a root. Does it have to be a root? Yeah, before you can find out. Before you can find out, I'm pretty sure you can find out, okay? Before you can find out if there are integer roots for All right, that's what we're going to try and do. Okay, I'm going to try and refine the idea a bit more clearly. Think about it a bit more, but that's what we want to try and do. Okay, we want to generate a list of vectors, a vector of random numbers generated using a polynomial, and then you are going to. Oh yeah. I'm so sorry. Okay, can someone, let's start with this. Okay, it'll be a lot clearer. Unless you have a problem with this polynomial and x squared or quadratic notation, you should let me know, and then we won't go down that road. But it's actually quite easy. I can explain every step of the way. If you're happy with this, someone pick up the screen and start coding. It's going to be from scratch. Just start with an empty main, and we can code you through this. Hey, Fernando, welcome to class. Are you able to take the screen? Fernando, can
Yes.
you? Hey, your microphone is switched off or something.
Yeah, I can hear you.
Do you want to take the screen?
Maybe later.
Maybe later. Okay, Fernando, I was talking about you before you came to class. Okay, you got to be on time, and you got to watch all of the videos, and get up to everybody on track. Okay, all of you, get in touch with the other students too. And I know that some of you are close to completing all of the quests. Hey June, congratulations. I think, are you done already? I saw you were very close to quest 9, wrapping up quest 9 yesterday. June?
Yes, Professor. Yes, I have finished the question 9, but I found the question 10. It is
No, there's no question.
option.
Nine is the last.
Oh, sorry. So there is the 10th question. So it is optional, or we need to.
What is optional? Well, no, I'm sorry. What is it?
Sorry. In the great page, there is only 9.
Only 9 for cs2a.
Okay.
Right. So if you've completed all of those, that's fine. What you should do is, even though you can just keep going on and complete all the green, right? You can, because green is cs2b. If you're going to be in my cs2b, you get credit for this and 2b, right? You can do that if you want, but I would encourage you to wait until later and before you start the green, because other students are still working on the earlier quest, and we can do with your help. Okay. So please help all the other students who are stuck and ask in the forums, if you don't mind.
Okay.
All right, don't go into green yet. All of you, okay? Anyone who completes green quest 9 before week 12, please don't go off and do your green quest. No hurry, okay? It's not a race. Just stick around and help all the other students also complete quest 9. Thank you so much for that. So I know a lot of people have reached or getting close to quest 9, which is good, but it's not being reflected in the forums. So I'm pretty sure all of you are active participants in class. You'll all get points for the half of the participation that is due for, that comes from class participation. All of you are good as far as attendance here goes. But as far as participation on the Reddit, that's 7.5 of the other points, the other 7.5 participation points. Only some of you who have actually contributed on Reddit reasonably get any of those points. Okay, those of you who are not active on Reddit and didn't contribute much to discussions, you won't get any of those 7.5 points, which means the maximum you can get is 93.5, right? And 92.5 in cs2a, unless you actually step up your game and be more vocal, like Zane and Kaylee and Ashwath. I've seen a lot of people ban there, but overall it's quiet. Even when Keenan or someone posts some code saying this is what we did, I got extra credit for debugging this, nobody even picks up the offer like that. And you're all if you're majoring in computer science, I would expect you to jump on offers like that, especially if you're getting extra credit for things like that, right? So if you're not active on the sub, you won't get any of those 7.5 points. All right, so if someone can pick up the screen and start coding, we'll start with this, okay? I'll set up the vector for you, and then you can do the later things. So in fact, I'll set up the shell of the code, and then you can take it up from there, okay? So, and I'll tell you how to solve it too. And then you can, well, I can go into as much mathematical detail as you want, but preferably, you probably know most of it, or you can help each other too, that's perfectly fine. Can someone pick up the screen, please? And I would just basically walk you through the code every step of the way. You don't have anything to worry. Okay, so you're basically just going to double as my, a laptop screen, because that I found works much better than if I were to type. Then the pacing is not so good.
So I do have some bad Wi-Fi still, I think. At least I could take up the screen if you want to try again.
You could try, Van. Thank you very much. Yeah.
Okay. Wait, what was that command for getting a incognito again?
Okay. Is this a Mac or a Windows?
Control Shift M.
What was that?
Control Shift M.
Hey, Noah, is it a microphone in front of you? It's like a a radio station microphone. Was this your water bottle? Oh wow. Yeah. And it looks like one of those DJ microphones. Oh, no, they have that thing there in front. No success, Van?
Just about ready.
So what we want to do once Van gets a screen up is essentially in the vector, let's say a vector of 1 million items. Okay, we'll create a vector of 1 million numbers. I think it'll complete, even on coding rooms. I think, yeah, let's do 100,000. Okay, let's not tax the machine more than we need to. 100,000 numbers, a vector of 100,000 numbers. And then, yeah, great, thank you. Just hash include, using namespace, and then I use hash include vector also, because we're going to be using a vector. Everybody okay with this so far? People should speak up, okay? People should speak up, and I'm depending on you to slow me down or ask questions and so on. Yeah, using namespace also.
Namespace.
Yeah. And you can get rid of the previous hash include line. I don't think the hash include. Yeah, that's right. All right, that's good. Thank you. All right, so in main, let's put a comment there. Yeah, get rid of all that. Leave the return. Yeah, all right. We'll put a comment in main. All right, you want to do that? Okay. So this is going. Yeah, put a comment above main. Oh, in main. That's fine. Yeah, where you are, it's fine. Because next line and then add a comment. Yeah, there you go. Tab in and put a comment. Tab in. Yeah, put a comment. And you can say create a vector of 100,000 integers. Using an equation of the form x squared plus bx plus c. Yeah.
Sorry, the audio cut. What was that after integers?
Using an equation, using an expression of the form, and go on to the next line. I think that's 80 columns or so for now. Form n squared plus bn plus c. N squared plus bn plus c. And yeah, that's right. N squared plus bn plus c. Right, I'm just using n squared instead of x squared. Okay, it's just a quadratic. To emphasize the fact that it is not continuous, it's a discrete variable. N squared plus bn plus c. Bn plus c, where b and c will be randomly chosen integers between 0 and 10, where b and c will be
integers.
Where b and c will be, b and c will be randomly chosen integers. In the range 0 to 10. Yeah. Okay. All right. Now let's pick B on the next line. and you say int b equals on the next line, on the next line.
Mhm.
You say size t b equals, we'll just keep everything positive. Size t b equals rand %10, and size tc equals rand %10 also. And then you can insert an srand call right at the beginning of main, so we don't always get the same random numbers.
Yeah, rand %10, would that be
Oh, I see.
Anyway.
Percent sign. Shift 5, I think.
shift? Yeah, gotcha.
Space 10. Space 10. And then the same thing for C also. Oh, you
Okay,
need a semicolon at the previous line, and
gotcha. And then C for what?
same.
Gotcha.
And then as soon as you enter main, insert a call to srand, which we'll leave commented out for now while debugging, but we can uncomment it after debugging. After you enter main on line 8, enter, hit enter on line 8. Yeah, and then insert a call to srand, srand.
Sure.
Open parentheses, and then say time, open parentheses.
Like inside of the
Inside time.
Gotcha.
Yeah. Just get into the habit of doing that line very often, because it's standard. Everybody does that, and it's good to have as a automatic response. Inside, say time, time.
Oh, you mean like an extra space on?
No, inside the parentheses, say time.
Okay, so wait,
So that's what I mean.
time?
That idiom, that pattern is very useful to remember, because you can just plug it in from your memory. Time, time.
Mhm.
And then open parentheses. And then 0 uppercase L close parentheses, I think. Oh, you don't need close parentheses. 0 uppercase L is fine. Okay, because the close is already there. Put a semicolon at the very end. Right. And the one thing we need to do is time returns a signed quantity for historical reasons. So you just have to tell srand, even though time returns signed, we want unsigned part. So put unsigned in parentheses before T, put unsigned, the word unsigned inside of parentheses.
Gotcha.
No, it has to be inside of its own parentheses.
Oh, it's like, so encapsulating.
Casting. Yeah, we're just typecasting whatever time returns. Whether it's a character or integer or long, we're just saying we just make it an unsigned integer, because that's what it's trying to.
So close parentheses goes on the other
right
side
there,
of
right
this
there.
Gotcha.
Okay, and then put enter after that line.
Enter. Okay.
Enter after, and then comment this line out. And say uncomment after debugging. Right, uncomment after debugging.
Gotcha.
This line out and put a comment at the very end saying uncomment after debugging. So this is standard practice. You can remind yourself to do this, right? Even in code that you write. So put a comment there, yeah, saying uncomment after debugging. Okay, now let's set up our vector. After line 15, hit enter. Now say vector open angle string open angle size t, a vector of size t, vector of unsigned integers. Angle. No, angle bracket. The less than sign, not square bracket.
Sorry, audio cut again. So
Sorry. So get rid of the square brackets.
Gotcha. So square brackets.
Yeah, and then put the angle sign. I keep saying angle sign. It's less than. Angle brackets.
Oh.
Size t. Let's make it a vector of size t.
Okay, gotcha.
Make it a vector of integers. Not size t. Integers.
Gotcha.
No. Vector inside of angle brackets should be integers. Vector is just fine. You had it like right before.
Like so. Okay. So just like this.
Yeah, and get rid of the space before the vector.
Gotcha. Okay. So that's kind of like saying like int variable, but this is like vector int.
Yeah. It's a vector of integers, vector of strings, vector of something.
So that's how you like declare a vector.
That declares your vector.
Gotcha. Okay.
Right. Space, and say vec or something like that. Give it a name, VEC.
Good. You say what? Oh,
VEC.
Perfect.
VEC. Open parentheses. And say 100 times 1000. Okay, 100 times 1000 right there.
Gotcha.
Times. Okay. All right. Now put a semicolon at the end, and then put a comment saying this is a vector of 100,000 elements. Right. In fact, if you want to make it more readable, you can actually make a vector size a constant size t on the previous line. This might be a better way to do it on line 16. Say enter. Yeah. Yeah. You say const. No comment. You just say const. No. You just say
Sure.
const. Space size t. Space vec underscore size all uppercase. Make them all uppercase because it's a const, right? Yeah, all
What, this
space size t space vec underscore size equals 100 times 1000. 100 times 1000. Okay, now it's self-documenting. We don't even need a comment now, right? Put a semicolon there, and on the next line, instead of 100 times 1000, just use vec underscore size.
Okay.
Yeah, everybody okay with that? Okay, now all we need to do is just do a loop, and so start a loop after that. A blank line, yeah, there you go. So for size t I equals 0, I less than vec underscore size, I plus plus.
So
in fact, even better, instead of I, let's just use n, because that also ties in with our comment before.
You say n
equals 0. Oh no, not size t equals 0. Size t n equals 0. Size t space n equals 0.
Gotcha.
Yeah, and then after the semicolon, you say n less than vec underscore size. Yeah, and put some spaces around the less than and before the n also. Yeah, it's easier to just clean up as we type. I know we can also come back and tidy it up. It's easier this way, I think. Right, a semicolon n plus plus. Right, so on the next line, you're simply going to say vec square bracket n equals what is it, n times n squared, right? N times n is n squared. In this case, what we'll do is see, again, we're going to break a rule here just for aesthetic purposes, and you can feel free to do it differently if you think. This is so here, put the n star n together just to say that it's 1 unit, n squared, right? N star n, no space around the, because we're just helping fellow programmers by saying n star n is 1 unit, right? So now we can say plus space plus space, right? No, and instead of the semicolon, get rid of the semicolon. No, get rid of the semicolon. Hey, this is our quadratic.
Oh, we're doing the equation. Okay, got you guys.
Yeah.
So
plus b star n. Again, b star n, no spaces around the star. Plus b star n.
B star n plus
c. In fact, let's make it more complicated than this. Let's say minus b star n plus c, and then change the comment also to say that our equation is going to be n squared minus bn plus c, right?
Sure. Okay.
Okay. All right. Now, on the next line after the for loop, one more blank line and go to the outside the for loop, outside the Now put a comment there. And say at this point, vec has 100,000 numbers that were generated using the quadratic equation above, something like that. Okay. Now we would have a loop. Now we can have a user interaction loop where the user will type in a number, same as what you did before. All right, you're going to have a loop saying type in a number, and the user punches in a number, and you're going to search the vector and say, does this vector contain the number or not, and get the return. Okay, that's all you're going to do. However, in this case, you can do some clever things. You can either search the whole vector, 100,000 elements, or you can search the first few elements, find out what B and C is supposed to be, okay, and then find out if can you solve that equation with I think it should be possible. It should be possible. Okay, it should be possible. I'll leave you to figure it out, but I think it is possible. You have all the information, right? Once you know the values of B and C, you can find out if there is some value of n for which you get that number. Yes.
See, I think.
Because essentially what you have is that you have x squared. Let's say B and C are 3 and 4. Our equation is going to be x squared minus 3x plus 4. Yes. Or n squared minus 3n plus 4. That's our equation.
Yeah.
Okay. All right. Now suppose I came to you with a number. Let me get more of you on screen so I can see nodding heads if necessary. Okay. Suppose I came to you with a number saying, does this vector contain the number 4,000? okay, you know that the vector has numbers. You know by looking at the first few elements that B and C are 3 and 4. You found out, right? You can solve that, right? Do you know how to solve that? I can show you how to solve that if you want, right? Set up the rest of the things. Set up the rest of the things, and I can show you how to solve that. Okay, it's very simple. All you need to do is there's only B and C, only two magic numbers you need to discover. Yes, because you know it is everything is generated using a polynomial that only has these two coefficients that you need to discover. Everything else is known. So how many of the vector elements do you need to examine in order to discover those two numbers? Because there are two unknowns, you only need two of those elements. Yes?
Yeah, there's two variables.
Okay, so you know already. So you know n squared minus 3n plus 4 equals the first number. Maybe the first number is 12. Yes? And then the second number also, you know. So you can plug in the value of n. N is 0, n is 1. So the only things that are missing here are B and C. You don't know the value, right? So you have B. In fact, it's very easy to find out, right? I shouldn't walk you through this, okay? In fact, if I dissect it step by step and tell you, I'm basically sucking out every drop of juice from this problem. Okay,
Wait,
so
Professor?
I shouldn't do this. Yes.
N is inputted by the user, or
No. N is your loop variable, right? You don't know. Thing is,
so
N
for
is what you
each
don't
iteration,
know.
though, starting at 0, and then goes to like, what is it?
okay,
100,000.
sorry, I wasn't looking at the loop. Yeah, my bad.
Yeah, I know.
I get it.
Yeah. So now I come to you with the number 4,000 and say, is this number in the vector or not? You have a choice. I can either search the entire vector, 100,000 elements, and tell me whether the number is there or not. That's one possibility. Yes, that's what you were doing on Tuesday. Yes.
Yeah.
Okay. Now you're saying, well, I don't want to search the whole array. However, I know that every number here is of the form, x squared minus 3x plus 4. That much you've discovered by looking at the first two. Now all you're asking is that, is there a solution for x squared plus 3x plus 4 equals 4,000? Was 4,000 generated using some value for x, which is an integer? If I plugged in some value for x in this equation, x squared minus 3x plus 4, do I get 4,000 or not? That's the question you're asking. Yes? And you can solve that in constant time. You don't have to look through the array at all. Because then you're asking x squared minus 3x plus 4 equals 4,000 means x squared minus 3x minus 3,000 minus 4,004 equals 0. And solve it. You can solve it using, your quadratic methods, minus b plus or minus square root of b squared minus 4ac over 2a, right? That's your standard equation. So you solve it.
I somewhat follow. Are we supposed to? So you're saying like we're taking, are we taking an instance of one of the vector, like 0, 1, 2, 3 slots in the vector, and then comparing it to 4,000 to see if it hits 4,000?
Okay, all right. So let me flesh out more of this if you like. If you like, I can flesh it out. And also, don't worry, right? We can also talk a little bit about this on Tuesday if we don't complete this. But that doesn't mean you should put it off, right? I'm happy to talk more about this in the forums. Anything that we leave off, I'm happy to talk during an extra class if you want before Tuesday. But it's important to get this right. Okay, here's what we're trying to do. So go to your int main, above int main. Let's go start working on that function. Okay, start working on that function, right? Yeah, say there you say this is our function going to be, say bool is present, then say const int vector and then ampersand vector.
Am I supposed to put is present?
Yeah, the bool is present, that's fine, and then open parentheses.
Okay.
And then same signature as before, except not string, it's int, right? So it's going to be vector.
Wait, inside. Okay, so
inside. Those are the parameters. Vector.
You're talking like this.
No. Inside the parentheses. Go inside the parentheses.
Okay. So vector.
Okay, so say vector.
Vector.
Angle bracket int, right? Angle bracket int.
Gotcha.
right? Space, vec. No, ampersand vec. We'll pass the reference. Ampersand vec. No, space ampersand vec. Space ampersand vec.
What's ampersand?
Oh, shift 7.
Oh, yeah, okay, gotcha.
Vec.
Vec, okay.
No, you don't put a space there. It's not an operator. It is an operator, but not a binary operator. Okay, comma, yeah, space, int target.
Then space target.
Yeah. Okay, now make that a const vect int, not just a vect int. Just put a word const in front of vector.
Okay.
Not in vector, in front of vector.
Gotcha. So like right here. Yeah.
No, in vector, in front of the word vector, not the variable.
So like right here.
There.
Okay, gotcha.
Okay. Thanks. Right? Yeah, there's the extra space there. Yeah. All right, cool. Now put a space before the brace also to make it neater, cleaner. The opening brace. There you go. And then inside of here, what we're going to do is that we'll put a comment there. Also separate main out. Main should be, you have a blank line before that. Gotcha. Okay. So in this function, let's put a comment above this function saying what this function is going to do. Right. So when this function is called, right, we know that vec contains numbers that were generated using integer parameters for n.
Writing all this down. So when called.
So I see. When called, this function should return true if target. When called, this function should return true if target occurs in vec and false otherwise. If target occurs in vec or exists. Is everybody okay with this, right? We're typing this, and I want to make sure that everybody's on the same page, okay? I don't want to leave any people behind. If you get lost, for a few minutes and then find it hard to catch up, it'll be much harder to catch up later, okay? So let me know. It's important to have everybody in tow before we just keep marching ahead. So if you're dropping off, let me know. Exists in vec and false otherwise. Next line. Just yeah. I think this is 100 columns. I think intuitively it looks like 100 columns, but yeah. And false otherwise. Okay. On the next line, you say, however, we have some inside information or a gut feeling. Feelings, okay. Feelings, no, not emotional feelings, right? Gut feeling, okay. All right. Gut feeling that this vector only has numbers.
Yeah. Only has numbers?
Only has numbers that, on the next line, that were generated from an equation n squared minus 3x plus 4 for different values of integer n in n squared plus 3x plus 4. Okay, yeah, that's what we want to do.
Only has numbers that when generated, what was that? That
were generated.
Gotcha. That were generated.
Where WERE. Yeah, that were generated using the expression n squared minus 3x.
Was it?
We'll just say 3 and 4. Okay, we don't know 3 and 4. It's just B and C, but we'll assume 3 and 4. Okay, minus 3n plus 4.
Gotcha.
4. Okay, for various integer values of n, 0, 1, 2, 3, etc. Okay, and then you say 0, 1, 2, 3, etc.
What was that?
Comma or dash. You can say dash 0, 1, 2, etc. So people are, when you read the comment, you know exactly what the vector has. Yeah, n equals 0, 1, ... Yeah. Okay, is everybody okay with this so far? Okay, on the next line, you can say our strategy is going to be, right? Form the first equation. So our strategy is going to be, strategy one. We only have one strategy.
Yeah, I got you.
Okay.
Sorry, I'm not used to typing so much.
Yeah, you still have more strategies than I do. Right? It's one of our strategy. Oh, all right, you have many strategies. Okay, all right. Yeah, gonna be okay. B. Okay, on the next line.
Yeah.
All right. Form equation one by.
Sorry. Form equation.
Form equation one by plugging in. Form equation one like this. Okay, so you're gonna say n squared. Well, let's say the first element is 0, right? So 0 squared plus so 0 squared plus b times 0 plus c, right? Okay, so the first equation is going to be 0 squared plus b times 0 plus b times 0.
B times.
Yeah,
0.
b times 0 plus c,
Okay.
plus c.
Plus C. Gotcha.
C. That should equal our first vector element, right? That should equal our first vector element, isn't it?
Yeah.
Equals vec of 0. Equals vec of 0.
Hmm.
Equals space.
Yeah.
Vec of 0. Vec square bracket 0. No, not vec square bracket 0.
Oh, yeah.
Yeah.
Right. Yeah. Bracket. Parenthesis bracket or
Square bracket.
square bracket. That's this guy, right?
Yeah. 0. Yes or no? I want you to, right?
So everything.
And then you can say, this is inside information. We didn't know that, right? Because that's all inside information, that the first element is actually generated like that. Right?
So
even then we can find out, but I'll leave that until
okay, gotcha.
Okay. All right. So using that, we can find out what the value of C is, because 0 squared is 0, b times 0 is 0. So what that tells us is basically the first element is basically the value of C. Yes or no?
Yeah. So
okay, so using that, we now know the value of C. Oh, so next line. On the next line, that gives us the value of C. On the next line, that gives us what C should be. Right. In fact, change 3 and 4 to B and C on line 8, right? On line 8. Yeah, you got 3 and 4. Just change that to 3. Minus bn.
I'll go back to the equation.
And plus C.
Okay.
Okay. All right. So now I continue on with the comment on line 11. Enter. Right. Now from the second element of the vector, we can say this is all starting to look like mathematics, right? Even though it's computer science, but actually still, even though we're using math, again, think about it. We're just doing empirical methods here. This is all machine learning. It's not deductive, because we're just saying we're going to form a theory about what the quadratic is going to be and give the answer without exhaustively looking at the entire vector. Yes? So it's still not true mathematics. It is just empirical, I hope I'm right kind of reasoning, which is what science is. Okay.
Yeah.
All right. That's what machine learning is. So now from the second element, we can say on the next line, you can say n squared minus bn plus c equals vec of 1. And now change n to 1. So it's going to be 1 squared minus b times 1, right? It's going to be 1 squared.
Oh, right.
Yeah, I think b times 1.
B times 1. Oh, yeah, okay.
B times 1.
Yeah.
Equals vec of 1. Is everybody okay with that equation? Yes?
Wait, I have a quick question.
Yes,
on line 10 is the 0 to the power of 2. Is that supposed to be a minus next to the b?
Oh, yeah.
Yes. Thank you, Ali. Wow. Okay.
I was like looking over it.
Not a question. You're actually pointing out a typo. Thank you, Ali. And then we get the other equation correct. Yeah, 1 squared minus b times 1 plus c equals vector. Right. Now, does that equation, like equation 13, does that allow you to calculate b?
Yes.
Yeah. So now we
Yes,
know,
it's
just by examining the first two elements, we know what b and c are. Yes.
Yes.
Okay. Right. So now on the next line, write a comment. Right. So at this point, we should know both b and c. No, both. Yeah, both. No, not we should both know, right? We should know both. No, both. Know both, not about. We actually know the exact values, right? We know b and c. Okay, so we can say, so we can form an equation. So now we can form an equation with the target number. The next line. We say n squared minus bn plus c equals target. Equals target.
Right.
Now on the next line, you say, if the above equation has an integer valued solution for n, and n is under 100,000, which is vector size, which we don't have at this point in time, but it's actually vector.size, right? If if an integer valued solution for n, and that solution is less than vector.size, I think so, yeah. And I think so, yeah. Vec.size, no, lowercase vec. Oh yeah, all right. We don't have vec underscore size. We only have vec.size here. So you can say vec.size, yeah.
Gotcha. So vec under
dot
what?
size,
Dot
size, dot size.
Gotcha.
Open, close, open, close.
Mhm.
Right? Then on the next line, then that number would have been, that number would exist at the nth index of the given vector, according to our hypothesis.
Gotcha.
Does that make sense? That is our entire hypothesis, right? So now we've got a method by which we don't have to look at the entire vector, but we can make a reasonable decision about the presence or absence of a candidate in the vector by looking at the first few elements. Yes. And like Kaylee or Ali or someone pointed out, the more money you have, the more elements of the vector you can look at before you make your hypothesis, right? Because technically, in a real world problem, it's not like a simple parabola like this with just two variables, yes?
Mm-hmm.
In a real world solution, in a problem, you have many, many coefficients, right? It's actually a matrix, n-dimensional matrix, lots and lots of real numbers. Mm-hmm. And so, using some data, you can put the values on the most significant coefficients, like the cubic coefficients or high-powered coefficients. You can put numbers on those, but you need to collect a lot more data to put values and find values on the small coefficients and all. Yes.
Yeah.
So that's where people will say, well, if you're $1 billion company, you can invest a lot more in getting, these fine data points. But again, you got to invest cleverly and in investing in these fine data points, because the finer grain detail you get, the more likely they are to shift. What happens is that the sand at the bottom of a hill keeps shuffling all the time. Yes, it's at the top of the hill is more stable in a sense. So if you get to the fine detail, they're all changing, but the massive structure is usually the same. So the big values, so the bang for your buck, 90% of the machine learning dollars are usually well spent, because they give you the big parameters that are important in making decisions, right? You can turn left, turn right, that kind of, you can't turn left into a, one way and things like that. Those are important decisions, right? But you put a lot more money into it, you can get even more finer detail, right? This is a better time to turn, right? And things like that. So that's what distinguishes more data from less data. But again, we have to be careful about investing. You have only so much money. You got to say, instead of collecting all that data, I'll just collect this focused, targeted data. Those are the calls made by solid data engineers, not identifying this paradigm is great, this decision is the ultimate output. No, the best data engineers say their calls are, well, let's use this data set, okay? This data set is actually diluting the model. So, and the reason I say that is because 90% of the data comes from that source, which is not bias controlled, right? People didn't know that. And you basically just drew a graph and said, look, it's not a uniform distribution here. And so you have to compensate for the, for the peak or the mode in the data. Otherwise, that's going to contaminate the overall output. I don't know. I'm just talking about nonsense here, right? Things that don't even make sense to you right now. But or maybe it doesn't even make sense at all. But this is essentially the same insight. You're going to bring to bear is to say, how much of the vector am I going to look at? In this case, it's only a one-dimensional vector. But you can imagine you get a two-dimensional matrix. Yes. And say two-dimensional matrix, and it's not just B and C. I have more variables to find out.
Yeah.
So, all right. So, and I think this is a different search technique than linear search. We did linear search last time. Here, we're doing heuristic inferential search. It's not part of cs2a. It's not part of the syllabus. But, search techniques in general are. And I think, as this field is evolving and, we're talking about machine learning and AI and data science and things like that, I think it's important that, these search techniques are also in your radar. And then, this is, when we're searching, this is what we're doing, trying to do. In your linear search and binary search, we can give a deductive answer and say, yes, it's definitely there, definitely not there. Yes?
Yeah. Yeah.
Okay, it's computer science, true computer science. But sometimes you got to say that, okay, I've reached, the human limit, because, the computers can carry on the algorithm like a Turing machine for, infinite numbers of years. But as humans, we're, time limited in our life. So in order to get the answer within 10 minutes or 10 hours or 10 days or 10 years, I'm going to make some compromises and say, well, I'm not going to do the computer science way, but I'm going to cut some corners here. But these are intelligent corners, right? I don't cut, willy-nilly corners, but I say, I'm going to look at only this data, that one, or, I'm going to only model for this many parameters, not, A to Z, but A to X or A to B, those kinds of things. So that's what I've found, that, most of the time, when breakthroughs are made in machine learning in teams, not in big companies like IBM and all, but breakthroughs from teams come from people identifying better ways of doing the thing that we already do, rather than a brand new way altogether. And starting off as young engineers, I think it's always better. Again, I could be wrong, but you may find out. But this is a trusted way to keep marching ahead, is to not shoot for the big fruit right away in these things, and basically say, when I join a team, I'm going to try and look at ways to improve what's already being done, rather than I'm going to try and change everything. Because you do employ people that want to do that, not maliciously, but they have this zeal, a beginner enthusiasm. Say, I'm going to change everything and do this thing entirely differently, right? But it works better by trying to understand what other people are doing and trying to improve what they're doing, get better results. And in the process, you'll discover a whole new way of doing things that was even better than what you thought before. That's what I find, anyway, in my experience, okay? So that's what it is. Can you guys wrap up the rest of this code? This is very simple right now, isn't it? Yes? Do you know how to solve that equation? It's very easy. The formula for a quadratic, I can just tell you, write it in the comments, okay? You can look it up. You look it up on Wikipedia, right? How to solve a quadratic equation. In fact, your quadratic is even easier, right? Because it's all integer solutions and A is 0. A is 1. You only have B and C. Yes? And it's integer, which means you don't even need the quadratic. You can actually solve it by just completing the square. But just use the equation, you'll just get it computationally. And it'll be an integer. For sure, because that's how you're generating the numbers. It'll be an integer. So if you have any questions, you can call me. I'll come and help you, right? If not, I think this is eminently set up to be a fantastic problem for you guys to solve. And this is a fantastic search method you're implementing on day 2. Linear search, you've already got it in your pocket right now. Yes, you can do it in your sleep. Right now, this is not linear search. It is actually machine learning advanced search. You're trying to come up with a heuristic with some insider information. However, in this case, you got lucky because I told you it's a quadratic of the form, n squared minus bn plus c. But in the real world, you don't know. You don't know you don't even know if it's polynomial in the first place. All right? If you knew it was a polynomial, you can say that if it's a polynomial in the nth degree, you can say it's ax to the n plus bx to the n minus 1 plus cx to the n minus 2. So some really complex and long polynomial. right? So it's got like 15,000 different, coefficients you got to discover. It's painful, right? But you'll do it. But it's a polynomial. But I told you. But what if you got given like that? But it's painful, but you got to do it, right? So many times you don't even know if it's a polynomial. Maybe it's exponential. Maybe it's some other function already, sine x or cos x. Even though they have polynomial expansions, we have infinite number of terms, right? So how do you discover that? So sometimes you have to have a machine learning technique. That's where the data engineer comes in, right? The data engineer comes in, looks at the data, and says, well, this data couldn't possibly have been generated by a polynomial generator, right? Whatever natural process was generating this data was exponential in distribution, right? You've had people look at data and say that, right? You say, well, that doesn't look like it's naturally occurring. It looks like it's been artificially flattened. Or, this should be a naturally occurring Gaussian distribution, but it has two different modes. One on April 3rd, one on April 9th. It should only have one mode. How can we flatten this distribution, right? Discussions like that. So that's what data engineers do. And say, well, okay, now let's try and find out by isolating that and sending it into the system so that can identify what we should do to get a uniform distribution, something like that. Okay, so those are the ways in which we kind of do things. I think this sets the stage very nicely. I don't know how many of you are planning to do CS2b.
CS2b is coming up in spring quarter.
Yeah, I'm not teaching CS2b in spring. Mikkel McDaniel is teaching CS2b.
Okay, then, well, I mean, that's the plan. Yeah, if I can survive.
We offer 2B, 2C, we at Foothill, Python, Java, and C++. These three courses will get offered every single quarter. Okay, all sections.
Okay.
Every single quarter. But we have all these other classes that are more workforce oriented and some specialized classes like quality assurance and things like that. Those may not get offered every quarter, right? Those we have to find out if there's enough enrollment and students, and if we can find instructors. But these guys will get offered every time. Whether it's not me,
That's cool.
If it's not me, it will be someone else.
Okay.
I will be teaching CS2b again in fall. Oh, maybe in summer too. I don't know. Mikkel is a good teacher. You can do Mikkel's 2b and do my questing on the side if you want.
Gotcha. Oh, so did you design the questing site, or was that?
Yeah, I did. Yeah, in fact, I don't know. Maybe not to you guys, but I went over the story of how it came about in a previous YouTube video, in one of one of a CS2a. Yeah. So that's all. What time is it now? We have time? Do we have time? We have 10 minutes. Do you guys want to do this on your own? We can pick it up again. Hey, Van, can you save this coding rooms thing, and will you make sure to come back on Tuesday?
Yeah, I'll make sure it won't get scrapped by then. I'll send it to Reddit too, just in case someone wants to go with it.
And bring this back on Tuesday, and hopefully you would have done this, okay? You guys would have got together and completed this. And then on Tuesday, we can try a bit more. Actually, should we do this? Yeah, actually on Tuesday, what we'll do is what we're going to do, okay? We're going to do linked structures, because next week 10 and week 11, isn't it? Next 2 weeks are week 10 and 11.
I think next week is week 10.
Yeah, okay. All right. So we're going to do linked data structures next week. Okay. So you can see I'm already smiling, but it's all right. But linked data structures.
Oh, and sorry, isn't week 11 when we get this, we get the what's it, the second and second?
Yeah, midterm retake.
Gotcha. Okay, so like at the beginning, is it gonna be like Monday, week 11? It'll open for a day or so. I don't know if we talked about that.
No, I haven't even opened it. You guys haven't got together yet. Someone should request. So one of you should request a retake, and then I'll open it up for everyone.
Oh, okay. So wait. So if we, okay. So
yeah, if nobody requests a retake, I'm not gonna do another one. Okay.
Oh, okay.
If they request a retake, should we do it on the Reddit forum and then anyone can comment?
Yes, yeah, you can do that. You can do that, or if you want to do that, yeah, that's even better, right? Because you can then do a poll and say, well, at least 2 people need it, so you can do it. All right, so you can do it.
Okay, that's cool. Is the midterm the only one we can request for a retake, or could we go?
Yeah, what else can you do a retake for?
What was that? Oh, there was the data representation quiz 1.
Yeah, that's fine. Okay, I'll retake that. I'll open that too. So both of them.
So we could do that one too.
You do, yeah, do a request for both of those.
Gotcha.
Just your final. You can't retake the final.
Okay, that was gonna be the next question.
Yeah. And then and if you've completed all the quests, hang on to them. You know, when you do my 2B, you'll just get credit for them. You got to do them all anyway in my 2B. Anyone who does my 2B has to do all the blue quests. So they get credit for it.
Mikhail, even Professor Mikhail?
No, not Mikhail, unfortunately not. He has his own system. Maybe he has something like questing. I don't know. Yeah, he created something when I was working on the questing system. He was also creating something. I think it was called Grade Oven. I think he created something called Grade Oven.
Grade Oven. Okay.
Yeah, I think and just like the questing system, you would submit your code into the Grade Oven and he'd bake it for you or something like that, right? So yeah, you can expect different experience, right? It doesn't all have to be in the jungle with wild animals. So you can be a baker for a quarter. But you still have these, and if you come back to my 2B, you'll get credit. But you got to do the green quests anyway to get into my 2C. I would highly encourage some of you, all of you, in fact, to do my cs2c in spring. No, not spring. No, that's next quarter.
It'll be fall, or would it be winter?
Yeah, can you fall? Oh, gee, I'm not teaching the cs2c again until. I'll request if there's sufficient enrollment, I'll request a cs2c section in fall. Even if if you finish cs2b and want to do it's not going to work in summer, because in summer what happens if I offer cs2c is that there's a whole bunch of high school students who are just after the achievement and another feather in their cap. I think from the looks of it, maybe not true, maybe they're really invested in the subject too.
I mean, if they can make it all the way to 2C, then I think that kind of weeds them out.
But shouldn't do it over summer. Previously I offered over summer cs2c, and a whole bunch of high school students did it. And I could tell they were not really enjoying it. They were just basically competing with each other, finding solutions off the net, maybe just getting through it. And I don't know, saying I completed everything in 6 weeks. Nobody gets anything out of it. Because in the end, I don't even know if they actually got something out of it, or whether it was them or Adderall or something else that did it for them. Who knows, right? So 2C is not a success, in my opinion, in summer. Okay, you need, if I say that even 2B is hard to enjoy in summer, really enjoy. 2A is okay. You can easily enjoy 2A in summer. 2B is harder to enjoy in summer. 2C I think is practically impossible unless you're already a professional coder. Okay, if you're out there in the industry, you're a Python or a Java coder already, programming, and then you say I want to learn the C++ way of doing things. Okay, those guys can have a good time and enjoy cs2c over the summer break, because they just get a piece of paper and they also get to pick up C++ on the way. That's why, I think last year, one of my students, Chris or someone, sent me an email saying, what do you think of all these boot camps, right? Because they say, you learn C++ or game development or Unreal in 6 weeks, right? Or C++ in 3 months. And it costs like $25,000, $25,000 to $50,000. And so you finish this, we'll get a job for you guaranteed, or shit like that. But nobody's going to learn C++, and if you don't already know programming, you're not going to learn it in 6 weeks. I can guarantee that, right? Not in 3 months even. Because even if you're like Albert Einstein working through everything, it's just a question of familiarity, right? Unless you already downloaded all the experience from someone else, like Neo in the Matrix, you got to face these and learn. If I drive onto the left here, that's what's going to happen. You see that firsthand. And in order to experience firsthand all these situations, even if you say, I'm not going to spend a lot of time thinking about it, I'm just going to experience it and move on, right? Just the sheer number of those experiences, add them one second up, it's still going to be more than 3 months. So as anyone who says I've mastered C++ in 3 months, that they're essentially saying I already knew programming before I came in, okay? And in summer, it's not even 3 months, it's 2 months. It's 6 weeks, it's half of 3 months. There's no way you can do. Please don't enroll in courses other than 2A in summer. I don't know if in summer I'm offering 2B even. I'll talk to Beta, but certainly I would like you guys to come back. And if you all ask for a 2C section in fall, it has to be done in spring. Asking to be done in spring, because Beta will have to schedule it and it takes time because there's all these adjuncts involved. So let me know in a month or so, and then I'll ask for a 2C section. But it's fun. You guys are doing great. You're learning things. You're asking questions. That's the most important thing. Okay, giving answers is the easiest thing on earth, right? Asking questions is the hardest thing, and So you're asking questions and also not afraid to say, I don't understand it, go over it again. Because I can remember the millions of times when I was a student like you and I didn't know, but I was afraid to ask. And I never asked and I never found out the easy way. I had to find out the hard way, by painstaking trial and error. And
Got
not
a
that,
curiosity question, if you got a second.
Mhm.
For the equation that where this function thing, the is present, is there a way, is there an equation out there that will just not, no matter how many variables you'll throw at it, it won't find a pattern and it'll just kind of like constantly exist and like searching for something that you cannot form? Kind of like, like a pie.
That's a fantastic question. Okay. Actually, a fantastic question until the very last word. With pi, that's not true, right? Because with pi, it does have a very nice pattern, and you can technically infer it in two arbitrary levels of accuracy in finite time. Pi has a pattern, but you're talking about something that does not have a pattern at all.
Oh.
Yes, it is possible. That's how RAND is generated. How do we get the RAND function? RAND function doesn't have any pattern.
It exists somewhere in some cloud or something, and it like from 1 to like a big number, it's kind of just randomly sorted through.
Yeah, but how do we get that list in the first place?
It's sitting somewhere physically.
Yeah, but who made that? Who made that?
Some dude in the 60s, I think.
But how did he make that? How did he or she make that?
I think he manually put it in.
How did they manually put it in? How did they come up with these numbers?
He used the predecessor to some language.
No, it's not the language that gives you a number, right? It's some method, isn't it?
A method? Okay.
That no. By method, I don't mean a function. It's not a language that generates a number.
An actual method, yeah.
The procedure.
Yeah, procedure. That's a guess.
Procedure, and so someone came up with that because just by using a random procedure off, pull out of thin air, it's not going to work. You can try it. Okay, you'll see that it always has a mode. It look like a bell-shaped curve. They're all natural distributions you see are normally distributed, are all Gaussian. And the reason for that is a central limit theorem. No matter what the underlying, even if it's a really complicated, so sophisticated distribution, you get a lot of random numbers and add them all together, they're all going to be normally distributed again around the mean. So what you see around you is all bell-shaped curves. So if someone says, I don't want a bell-shaped curve, I want a flat, perfectly flat, uniform distribution, they got to do a lot of work to do that, yes? Because it's not naturally occurring.
I guess that makes sense.
Yeah, so it's really, that's why I say never mess around. All the newbie data science guys, I tell them don't mess around with RAND. Okay, that's one of the most precious resources that we have in the library, because it's not easy to generate a random like that. So that means that if someone gives you true randoms from RAND, there's no pattern, there's no mode, right?
I see.
So you can't tell. You got to search the whole thing. However, since we're past time, I'm taking the liberty of talking about these things. People can drop off if they want. Okay. However, if I took that elaborately engineered, cleverly constructed RAND function that some people in the Bell Labs wrote many decades ago, right? And I said, in my infinite stupidity, I said, this is not good enough for me. I'm going to mess with it and create a better random number generator. In fact, I need randoms that are 5 times as big as the ones that Bell Labs is giving me. So I'm going to generate 5 random numbers and add them all together to get a bigger random number. Yeah. I don't know, nobody's responding.
Oh, sorry. Wait. I was saying a hum, but I don't think the camera will cop that.
Suppose I came up with an apparently sophisticated and too clever for myself scheme that says I want a random number that's 5 times bigger than what AT&T can give me. So I'm going to take RAND output and add it 5 times, right? 5 randoms added together. That'll give me a random number that's 5 times as big. Yes or no?
Oh, yes.
Okay. So suppose I say as a noob, that's what I'm going to do to get my random numbers. I'm screwed, because then your is present will start becoming valuable because the distribution of numbers is not random anymore. If you look at the random that you generate, that is a sum of 5 different random numbers using RAND, it's not uniform anymore. You can plot, I can show you next class, okay? If you plot all the random numbers and histogram them, you'll actually see a bell-shaped curve.
What is, sorry, what does the bell-shaped curve represent again?
It is, the bell-shaped curve basically represents what is the number of random numbers you're generating in this range. So if you take the numbers from 0 to 100, yes?
Yeah.
If it is all random and I generate 1,000,000 random numbers, I can expect to have 1,000,000 divided by 100 is 10,000. So I can expect to have 10,000 random numbers that are equal to 1. I can expect to have another 10,000 that are equal to 2. In other words, each one of the 100 numbers are going to be represented equal number of times on average. Because yeah. No, I don't like okay. I don't like the word okay, because okay says you are right. You just say if you're okay with it, meaning you say that I agree or understand. Yeah. So
I say okay as in like I understand. Well, yeah, I guess I do say
okay. So because the previous time I heard it, it said that okay, you're right, I accept, and let's move on. Okay, I don't like that. I don't want to move on if I'm right and you don't see it. Okay.
I'm confused. Okay. But okay.
All right. So now what's happened is that it's not uniform anymore. We've taken what was a beautifully constructed uniform distribution and munged it so that it's not uniform. It's now scrunched up. Now, instead of 100 numbers, each of them having an equal likelihood, because it was uniform, every number occurred 10,000 times on average before.
Yes, I see.
Now I've squished up the distribution. It's now bell-shaped. That means the numbers in the range 40 to 60 occur more times. The corner numbers occur fewer times. 100 occurs fewer times and 1 occurs fewer times, but the middle numbers occur more times.
And this occurrence occurs more often because you cut the
because no, that is, well, it occurs because what's going on is that you took the uniform distribution, right, and then added all those numbers, through many of those numbers together. Therefore, there are more numbers that in the middle that don't get balanced out. This number here will get balanced out by that number. And since they're both equally likely, multiple occurrences of these guys will cancel each other out. But multiple occurrences of guys in the middle don't cancel each other out. They just average somewhere in the middle.
Okay.
That's the intuition. That's the intuition behind the central limit theorem.
Okay.
So if you're at the periphery, you will not be canceled out by the other guy. You'll still be like there, low there. Okay. But the middle guys, they'll tend to occur a lot of times. So the average, if you're taking just the averages will skew towards the middle, because these guys are the result of averages. Everything is a result of an average, but these guys are the results of averages of low numbers and high numbers, right? Or all low numbers.
Yes, I get that. Yes.
So that is why you get a bell shape. That is why everything is bell shaped in real life, right? Like if you say your grades, if you take a standard distribution for SAT scores and things like that, they'll see a bell shape curve. That's what they look at to normalize things, right?
Gotcha.
Populations, they say it should be normal. That's what they say. That's why it's called the normal distribution in statistics, right?
That is very interesting.
That's normal. Yeah, it's normal, meaning it's bell shaped. That's what you expect. So if you look at the scores, you'll see a lot of students, 2 standard deviations out. No, not a lot of students. Some very few students, very poorly, getting between 0 and 100, right? And then you'll see very few students who basically ace the SAT.
Yes.
Right? They'll be out here.
Yes.
But the bulk of the students will be here.
Gotcha. Right in the middle.
Right? So that's the bell-shaped curve. And that's the result of averaging. Averaging always results in bell shapes.
I see.
Averaging of multiple distributions. Yeah. And that's why it's called normal, because that is the normal thing that everything essentially converges to eventually.
Normal and average. Okay.
Was that useful?
No. I mean, like, especially I've always, especially, in college and stuff, everyone's saying bell shape this, bell shape that. And I kind of just nod along. I never really took the time to, dig a little deeper into the concept of like, what does it really mean? Especially, I mean, if I'm taking classes and it's being graded and stuff, I definitely want to know what that means for grades. But yeah, that makes a little more sense.
Yeah, and I think it's important to know.
Oh, it
Yeah,
should
I know
be.
people say bell-shaped curve and things like that. Essentially,
Yeah.
what they're saying is another name that you'll hear is Gaussian, because Gauss was a
This is
mathematician.
the electromagnetic man.
Yeah, this is the same guy.
Oh,
Carl Friedrich Gauss, Austrian or German, I forget.
I think Austrian. Yeah.
Yeah. So he was the one who investigated this curve a lot, and he was a prodigy. Even at the age of 9, he came up with very interesting and startling.
Yeah, we read about him. Kind of crazy.
Yeah. So it's called Gaussian. So some people will say Gaussian just to be fancy, maybe, I don't know. But
Yeah.
normal or bell-shaped is more common.
Oh, okay. So when they do say Gaussian, though, they are referring to
Yeah, different from Gaussian rifles, right?
Yeah,
But
just a smidge though.
yeah.
Okay, that's cool. Okay, so I do need to log up, and thank you for explaining that for me.
Thank you all for your patience and sticking around together. Fernando, thank you. By the way, your camera is totally off most of the class today, so make sure you're good there. And so see you on Tuesday, okay? And pick up the Reddit and make sure that Reddit is live, and help out the person who was posting about the CS Club before.
Gotcha. And I will I'll post the code we worked on today. And do we try and solve it by Tuesday, or were we supposed to
anytime? Right. And you can also ask me if you need more help, in solving it or the math of it, anything, right? Just ask me for an extra class and I'm happy to give you one before Tuesday.
Okay, I see. Gotcha. Okay, well, see you then.
All right, thank you all. All right, bye. See you on Tuesday.
Thank you. Bye.
Bye, June.
Mr.
Hi, Fernando. You good now?
Yeah. I haven't received a email from Sophie yet.
Oh, you haven't?
No, not yet.
Okay. How about this? Just send me an email. Is it 10 days? Because but she's back from vacation. She must have replied, or at least her assistant should have replied. Send me an email. Just remind me. Send me an email, and then I'll try and ask Ram if there's other avenues in which you can find out more about this. Okay.
Okay.
Ram is a dean, so he'll know for sure. He's on vacation, but even if he's on vacation, he'll respond to these things immediately.
Okay, Mr. Nand. Okay. Thank you.
All right. Thanks. Bye.